respiration and more. In this module you will see how heat behaves in water, learn how to solve some minor difficulties, discover what buoyancy is and how it varies, and examine some physiological aspects of diving and the effect they have on divers. Heat loss. You will certainly have noticed that if you stay for some time in the water, you begin to feel cold, even if the water felt warm when you first got in. To understand what happens, we must first learn what temperature is and its relationship to heat. Heat is a form of energy, and temperature is a measurement of the quality of heat that an object has. If we bring a warm and a cold object into contact with each other, the warm object will gradually give up its heat to the cold one until a situation of equilibrium is reached, meaning that both objects have the same temperature. The transfer of heat will occur faster or slower according to the thermal properties of the two objects. In our case, the warm object is our body and the cold one is our surrounding environment. When this environment is air, there is a moderate transfer of heat, because air, if it is trapped by our clothes, is not a good conductor of heat. In water, absorption and transfer of heat is much greater. In order to heat a given volume of water by 1 degree, we need 4 times more heat than we need to heat the same volume of air. Furthermore, the transfer of heat in water between one molecule and another is about 20 to 25 times more efficient than in air. We therefore get colder in water quicker than we do in air of the same temperature, so as divers we have to wear particular equipment that limits the body's heat loss. Wetsuits and accessories. The way we usually reduce the body's heat loss is by trapping a thin layer of air next to our skin by wearing clothes. The body only has to heat the thin layer of trapped air until a thermal equilibrium is reached. This, however, is not efficient in water because of the greater thermal conductivity of water and because the material our clothes are made of does not isolate us from the surrounding environment, and water will soak into the clothes. Divers use wetsuits to prevent this heat loss. These are types of overalls made of special material that limits the heat loss. The insulating material used for wetsuits is usually neoprene, which is a synthetic foam that traps tiny bubbles of air or nitrogen inside. These gases, which are bad conductors of heat, greatly reduce the heat exchange between the layer of air or water in contact with the skin and the surrounding water. The thicker the foam, the greater the insulating property. The type of material used and its thickness depends mainly on the temperature of the water and the length of time of the dive. Wetsuits also protect divers from scratches and abrasions and animals that can sting, as well as providing protection against sunburn while swimming on the surface. If the water is above 30 degrees Celsius, 86 degrees Fahrenheit, it is enough to wear just a dive skin. This type of suit is usually made of lycra, which also has the advantage of being elastic. Between 28 and 30 degrees Celsius, 82 to 86 degrees Fahrenheit, other materials can be used which afford greater thermal protection. In water lower than 28 degrees Celsius, 82 degrees Fahrenheit, it is necessary to wear a wetsuit made of neoprene foam. If the water temperature is between 25 and 28 degrees Celsius, 77 to 82 degrees Fahrenheit, you can use a one-piece 3mm 0.12-inch wetsuit. The wetsuit is called one-piece or a full body suit because just one piece covers the entire body. In water temperatures between 21 and 25 degrees Celsius, 70 to 77 degrees Fahrenheit, it becomes necessary to wear a wetsuit that is 5mm, 0.2 inches thick. There is also a one-piece version of this suit on the market, but many divers prefer a two-piece version. This consists of a full bodysuit and a shorty, or a bib overall set of pants and a jacket. Weak points of wetsuits are the zips, which let cold water into the suit. This is why many freedivers prefer to use very snug-fitting wetsuits without zips. However, these types of suits have the disadvantage of being much more difficult to put on. If the temperature of the water is between 17 and 21 degrees Celsius, 60 to 70 degrees Fahrenheit, you should use a suit with a dry zip, which doesn't let water in. These suits are called semi-dry and are made of thicker neoprene foam, such as 6 to 7 mm, 0.25 to 0.28 inches. For lower water temperatures, there are completely dry suits, which do not allow any water at all to get inside. The insulating action of these types of suits is provided mainly by the air trapped inside and the clothes worn under them. However, these types of suits must be fitted with a special inflation-deflation system. The best criterion for choosing a wetsuit is that it must fit snugly without being too tight. When necessary, hands and feet should also be protected by wearing neoprene gloves and booties. Hoods, which protect the head, may be a separate item or part of the wetsuit. It is important that a hood fits snugly, but that it is not too tight around the neck, as this may cause you to feel nauseous or make you feel as if you are suffocating. Above all, a tight hood may cause an incorrect reading of the arterial pressure to be transmitted to the natural receptors in carotid artery, which could lead to collapse. Thermal imbalances. Even if you wear a wetsuit, you still lose heat in the water. One of the first symptoms of feeling cold is shivering. This should never be ignored because you lose heat much more quickly in water. Shivering is an evident sign that you must get out of the water immediately, get warm, dry off, change into dry clothes, and drink warm fluids without alcohol or caffeine. The opposite problem could also occur. The wetsuit also maintains its insulating property in air. Staying in the sun wearing a wetsuit can easily cause your body to overheat, and this can lead to heat exhaustion or even sunstroke. To cool off, jump in the water or wet the suit. To prevent thermal imbalances, don't ignore your body's warning signals. Buoyancy. If you jump into the water with a wetsuit on, you will realize that it is much easier to float than when you are wearing just a costume. Let's discover why that is. Matter is characterized by its density. By comparing it with water, it may have a greater or lesser density. On the basis of this fact, we will have different conditions of buoyancy. Let's make a practical example by immersing a plastic bottle full of air in water. The bottle tends to rise to the surface. It is said to have positive buoyancy. If we fill the same bottle with sand and take it under the water, it will tend to sink. It is said to have negative buoyancy. The same bottle filled with water tends to stay at the depth it is immersed. It is said to have neutral buoyancy. This phenomenon is quantified by Archimedes' principle. Any object immersed in a fluid will receive an upthrust equal to the weight of the fluid it displaces. When we immerse an object in water, it displaces an equal volume of liquid. Now let's compare the weight of an object with the weight of the volume of water it displaces. If an object weighs less than the weight of the water it displaces, the difference between the upthrust and the weight of the object causes the object to float. If an object weighs more than the water it displaces, the difference between the weight of the object and the upthrust will cause the object to sink. If an object weighs the same as the water it displaces, it will be neutrally buoyant. Now you know why you float more when you are wearing a wetsuit. Thousands of minute gas bubbles, which are lighter than water, are trapped in the neoprene foam and therefore make you more buoyant. But these gas bubbles are compressible. As you go deeper and the pressure increases, the volume of these bubbles decreases and reduces the volume of water displaced by the wetsuit. Consequently, the buoyancy of the wetsuit will also become less. However, if you try to go under the water in just a wetsuit, you will discover that you are positively buoyant at all depths. To dive under the water without too much effort, you need to wear weights. Weights. Let's now examine this essential component of our diving equipment. A traditional weight system is composed of a nylon belt with a metal or plastic buckle. The buckle must be of the quick release type that can be operated by just one hand. Lead weights of different sizes and shapes can be threaded onto the belt. To prevent the weights slipping up and down the belt, they must be held in place using weight stops, or if you don't have weight stops, there are a few tricks you can use. Your instructor will teach you the correct way to don a weight belt. It is important that the buckle is always on the left, and that once the belt has been closed, the free end is not too long or too short. This guarantees that, in case of necessity, anyone can easily unbuckle the belt. When handling the weight belt, always remember to hold on to the end without the buckle to prevent any weights from slipping off. There are many different types of weight systems, and in some cases the weights may be integrated with other components of our diving equipment. Whatever types of weights are used, it is important that there is a quick release system. Respiration. Let's now examine some physiological aspects of the human body. One gas in particular is indispensable to the cells for metabolism: oxygen. We use our respiratory and circulatory systems, of which the main organs are our lungs and heart, to transport oxygen to the cells. The heart is nothing more than a pump that pushes the blood around our bodies through a network of blood vessels. Heartbeats are a succession of contractions and expansions of the compartments of the heart muscle. Thanks to this muscle and a system of valves, blood is pushed by the heart pump into the two blood streams. Blood from the heart flows into the arteries, which then divide into secondary vessels and continue to divide further until they become microscopic vessels known as capillaries. The walls of these capillaries are so thin oxygen can pass through them into the cells, and the cells can give up carbon dioxide, which is a waste product of metabolism. Blood-pouring oxygen is drawn by the heart through the veins and pumped into the pulmonary artery to the lungs, where carbon dioxide is exchanged for oxygen. Oxygenated blood returns to the heart through the pulmonary veins and is then pumped again into the arteries to begin a new cycle. Lungs are made up of minute sacs called alveoli, where the air we breathe in is separated from the blood by walls that are so thin that they allow gas exchange to take place. The blood gives up molecules of carbon dioxide through these walls and is enriched with molecules of oxygen. This gas exchange is essential for our life. Oxygen is transported in the blood efficiently thanks to the presence of hemoglobin, to which it binds strongly in the lungs and then gives up to the various cells. This marvellous system would be of little or no use if we didn't renew the air in our lungs by breathing in and out. Breathlessness, hyperventilation, and shallow water blackout. So breathing correctly is important. However, sometimes we get breathless and take a succession of fast, superficial, and involuntary breaths. Let's find out why. When we breathe normally, we use a minimum part of our lung volume, just half a litre or quart of a total capacity that can vary from 5 to 8 litres or quarts. Before the air we inhale arrives in the operative area of the alveoli, it travels through a series of rigid cavities, the nose and mouth, pharynx, larynx, trachea, bronchi, etc., where gas exchange does not take place. For this reason, these spaces are known as dead air spaces. The volume of these spaces is around 0.15 to 0.20 litres or quarts. Therefore, every time we inhale, the first air that arrives in our lungs is the air we exhaled the last time we breathed out, and which stayed in the dead air spaces. This air does not increase the oxygen content in the lungs. Instead, breathing more deeply improves respiratory efficiency because it increases the volume of fresh air we inhale with each breath. Although our bodies burn oxygen, the main stimulus to breathe is activated by the amount of carbon dioxide there is in our blood. If respiration is superficial, it is not very efficient, and the amount of carbon dioxide we eliminate is not enough to slow down the stimulus to breath. In this way, a vicious cycle is created that makes you breathe faster and superficially and gives you a sensation of air starvation. You are out of breath. To overcome this difficulty, stop the activity making you breathless and take deep breaths and try to expel as much air as possible from your lungs. This helps to eliminate the excess carbon dioxide and take in a larger quantity of oxygen. These deep breaths, with prolonged expiration, that help you overcome an attack of breathlessness are similar to those that the free diving record holders make before they descend, but the objective is different. In both cases, these deep breaths are made to lower the level of carbon dioxide in the blood. However, in a case of breathlessness, it is to bring the level back to normal, while with hyperventilation, this is the technical name for this method of breathing, free divers try to get the level as low as possible, well below the normal level, so as to delay the stimulus to breath. Contrary to what you might expect, hyperventilation does not significantly increase the oxygen content in the lungs or blood. Therefore, hyperventilation does not increase the amount of oxygen available, but it only delays the stimulus to breathe. Prolonged hyperventilation can therefore be dangerous, because the level of oxygen may get very low before the level of carbon dioxide stimulates the diver to breathe during a free dive. If the level of oxygen in the body is too low, it can cause us to black out or faint, which can obviously be extremely dangerous in the water. This type of blackout generally occurs in the last few meters, feet, towards the surface due to the fall in pressure. The best and easiest way of prolonging your free dives is to move calmly in the water and relax mentally. The safest way to free dive is to use the buddy system. Each diver should take it in turns to dive under the water, and while one diver is under, the other watches from the surface, ready to intervene if necessary. Obviously, the dives must be no deeper than the depth that can be reached easily by both divers. These few and simple rules make free diving safer and more fun. In the next module, you will learn how we can take the air we need with us under the water and the instruments that make it easy to use. Until the next time.